was how many ways successes and failures can be organized. So if you have something that you call a success and you want to change X right here. Okay, so here we know that this is a combination, right? So just a counting rule. N is the number of trials, X as the number of successes, P, and Q are the success and failure, right? Okay, let's take a look at what that looks like. We should write it down somewhere so that you keep this in mind. Maybe you want to write this part down. So let's go over here. Okay, again, we can use the StatCrunch. Okay, we have the overtime football. The total sample size is 460 games, and the probability P is find the probability of 250 wins or more. 250 wins or more. So really we're looking for a probability of, I mean the way you would write that, what you want to know what the probability is of a random variable capital X is going to be greater than or equal to, we can answer the question by finding the probability of 250 wins or more. In order to do the binomial, what are the rules first? What's the first rule for binomial? Numero uno. The first rule is that you have to have a situation of success and failure, no other choice. You remember that? And what else? Okay, so then we have to find, here's N and P and Q. So you're pretty well set. So now, what was the equation? The equation for the general probability of a random variable X, notice that's capital, is let's say equal to a little x, which is a particular outcome. Then that's going to be equal to, what's that, was N, choose X, P raised to the X, and then we have Q, which is a failure, and that's equal to 9 N minus X. Okay. So now let's take a look at this, and maybe we can even use the calculator on StatCrunch. Let's see. So okay, so N is 460. There's a failure. It's 50-50 in it. And then the formula is not practical because we'd have to apply. We'd have to do that. And look at that. What we'd have to do. We'd have to calculate what if we do it like with this. In this case, we would have to do what? You'd have to take. You'd have to calculate all of these. You'd have to calculate the probability that the random variable X is equal to 252, right? Plus random variable, the probability of the random variable X equaling 253, plus dot dot plus, right? All the way, keep going until you find what the probability of X is equal to a total of 460. Okay, so that's a lot of work. Do you understand? I'm calculating this out of each number bigger than 252. Now, you could subtract all of them, add them up to that point and subtract it from 1, but that's still 200. So table A1 doesn't apply because N is 460, which is beyond the scope of the table. So let's see if we can do that in StatCrunch. Okay, so it says we want the answer of the question, finding the probability that 252 wins or more in 460. Assume that the wins and losses are equally likely. That's why we have P equals Q. Okay? Now, let's see if I can find this. Sometimes there's a way. Oh, not like that. Okay. So, in the binomial, when you put it in, you see where it says that the total amount? That's all I had to enter, and the probability of a success. And results for the values are provided here. So do you see the 252? And that's listing it for every one. And I can't go down, but so this is saying it's a good thing you have technology. Okay, now you have a table just like you do for the normal distribution, but remember how we standardize it over 0? You can't really standardize this one, so they have several tables of different values of n and p, and so it's not necessarily very practical to do it that way. But let's try it. Let's try it. Let's see if we can get through this. So here they want, so you see the word exactly? That's pretty good because we're not asking for greater than or less. So we can apply to that equation directly. And then it says following circumstances. All right, so this is the table A1. N, choose X, remember? That N, choose X? This. Let me just to remind you, because when you look at the equation of the book, they don't have it in that format. They have it like this. N, choose X. And the way to write it out is N factorial over N minus X factorial, right? Divided by, okay, X factorial. That's what this means. Here you can put it right in front. You know what X factorial is? You multiply. But with a table, if you happen to have, n equals 5, well, that's good. And then you have to have P, right? And then there's the probability of the random variables, P of X. That's different than just the P. And then it says, at least 2 successes mean that the number of successes is 2 or 3 or 4 or 5. Remember the rule of OR is addition, right? And assuming that there's not mutually exclusive, we just add up the probabilities of each one of those. And that's what I told you to do. Let's see if we can do this thing. See, there's a way that you can actually look at the data to get the data here. And it says the one with the overtime rule. Do we have data of the overtime rule? I think that was that one. Let me take a quick look and try it. If not, we'll figure it out someday. Okay, now, somewhere around here, let's see. There's a place. Oh, I thought I was already logged. Oh, wait, I'm not there, am I? No, I want the data. Every bit of data in the book, in the text, is available here. So I'm just trying to remember how I picked it up. Okay. Oh, did you know that? Oh, there's a bar through it. Data available somewhere. Has anybody ever done it? Let's see, where is the data? Select a file on my computer. I'll work on it later. Let's not waste more time because I don't know. Data? Here's your hypothesis testing. I already said that was the binomial, right? So, and that was discrete. Now, the next one was the Poisson, and that should be a lot easier. But even so, let's say on that problem, that homework problem, actually we could do it. Because, let's see, the problem was in the textbook. I thought I had it already. That problem was, it didn't work out, did it? It's not exactly number 203. And this, let's see, make sure I got the right example. Okay, let's do this Tweeter one. You either have a Tweeter account or you don't, out of a selected sample, true? This part here, remember that was n factorial divided by n minus x factorial divided by x factorial. And they're saying that the probability is 0.85 of a success, right? Making a failure? What's the failure? It's 1 minus that, right? So we go here on, and okay, let's put that, because we need to remember this thing here. We got n, right? 5, 3, I go. So 5 and 3, and 8, 5. That's interesting because 5 plus 3 adds 8. 8 plus 5, and then 0.15. So let's try it. And they want to know what is the probability that x equals 3. Exactly. Given that there's 0.85 probability of a random selecting an adult from a dark room, and want to know if they have a Twitter account. What's the likelihood they have a Twitter account? Well, we find the probability, and there it is. Okay, so now let's see if we can get this number, right? That one right there. So we go to StatCrunch, and we go to StatCrunch, and so we go to, did you see that calculator? And now, here's our distributions. This is all you got to learn. You can pass the class, just memorize these. No, just kidding. It'll be more than that. What am I doing, a binomial? Okay, so what was n? I used to have like a keyboard here. Every day it's a little different. It's a random variable, isn't it? N is 5. And then, what do we want to know? Exactly what? We want to know, what's the probability of a drawing out of this class? Actually, in this class, how many of you use Twitter? 1, 2? Only 2 people? Oh, you're not following the probability correct. You don't tweet? Well, your president tweets all the time. Okay, so what I'm going to put here, look, I'm changing that to what? Do you see that? I changed it to equal. And now I put this one on, not 5, but 3, yeah? What was the answer? 0.138 is the problem. So that's easier. You could use it. You could put it in the equation. But I think a lot of you like the easy way. So let's see. The equation is, well, right there. So the probability, you can say it like this. The probability, something's wrong here. I knew it was wrong. It was like, well, every day is a little different. Let's see here. I tried to calibrate it, but then something popped up there and I couldn't hit it right. What the hell? Okay. So I write it like this. The probability of a random variable x is equal to 3. Okay? What you're seeing in the book is this. But it means that. Okay? So the answer is 0.138. So I'm just showing you it does exactly that. So I have n is what? What was n? 5. So then I have, okay, so I have, and of that I want to choose 3, right? Is that right? Oh, it's the wrong one. No, it is 3. I want to choose 3 out of 5. So now I'm going to have n factorial. Well, this is n. See it? So really what I'm going to be doing is this. N is 5. Choose 3. How many ways can 3 people be ordered among 5 people? That's what it's saying. And then I have P, which is 0.85. See it? The probability of success, 0.85. Yeah. And that's raised to the x, 3. Yeah. Yeah. And the Q, it's not Q. What's Q worth? Now I multiply times. This will multiply that times. Yeah. And that's raised to the 5 minus 3. That's a minus. Okay? So that makes it 2, right? So somebody has to figure out, well, let's say we got 5 factorial over 5 minus 3 factorial divided by 3 factorial. And then somebody will have to figure this out. 85 thirds, 3 power times 0.15 raised to the 2nd power. See it? What am I doing? This. The probability that the random variable takes on exactly the 3 value. But 5 factorial is written to 5, 4, 3, 2, 1, all multiplied together. And here's 3 factorial. 3, 2, 1. That's this guy. So look at that. But what do I still have left under here? A 2 factorial. Do you see it? So let me clean it up. You got a 5 times a 4, and down here we have a 2 factorial. What's 2 factorial equal to? Yeah, 2 times 1. 2, right? And so What do we have? Okay. So what do we got for that part? That's 10, right? Okay, so really what I have, this whole number here is 10. So I have the probability of x equals 3, yeah, is equal to 10 times whatever 0.85 to the third is times 0.15 to the 2. And I would hope that in the end it's going to come out to this value. Okay? That's it. Good. All right, so let's do the Poisson. And then we already talked about the standard normal, and then we did the binomial, and we worked with the uniform. Okay, so what I need is that Poisson. So starting at 5,1. Okay, this one is 215. See if it works. Okay, now. Okay, what does the binomial require? Either one or the other. It can't have any other choice. It's either winning or losing. Okay? So that's the first question you have to ask when you're solving a problem, to see which distribution it is and if it fits that distribution. So let's clear it out. And I don't need this term here. And now back to the book. Okay. So that was 215. There's a binomial. Oh, this is questions. There. Okay. You need to get this down. Now this is the equation for Poisson. Let me make it bigger. It doesn't seem like you can see very well. Oh, can you see it? Yeah? Okay, now. Is that discrete or continuous? Well, here's what needs to follow in order to use the Poisson. Remember the other one had to be win or lose? Okay, this one is a random variable x for the number of occurrences, and it works for some interval. So when you have a probability that you want to calculate and it's telling you that so many things happen in a certain time interval, you want Poisson. And then, well, the occurrence must be random, right? Random in quotes. And they have to be independent of each other. What's independent mean? What's an example of independence?
The outcome of one doesn't affect the outcome.
Good. And the occurrences must be uniformly distributed over the interval being used. All right, now, how did we find our mean generally? Now, if you look here, they're not even using our sample statistics, are they? They're saying we got directly God's truth. So they're saying that the deviation of a Poisson is equal to 1 times the square root. What is the distribution for, what is the equation if I wanted to calculate sigma, the S, normally when we think it's like a normal distribution? What's this equal to? Okay, so what we've been working from was this, x bar, do you remember from our sample? Is equal to adding up all the observations, do you remember that? And dividing by n, from I equals 1 to whatever n is. Remember little n? Well, this makes it kind of easier, because if you give you mu, you can find its deviation by finding the square root of mu. That's weird. The square root of the mean is the deviation of a Poisson. I don't know if you can appreciate that or not. That's weird. Now, and then they're saying that sigma, okay, now we had S, and that was the same thing, of I equals 1 to n. And then for every little observation, this means add until, but in packages until you come to the nth term. So that's going to be minus x bar. Do you remember that? Squared divided by n and minus 1 square root. Okay? But this is different. It's saying that this is equal to that. And this is the mean. So let's take a look at an example of when you would use the Poisson distribution. In this case, they're talking about the occurrences over a certain time interval of hurricanes. Let's see. For a period of 55 years, since 1960, there were 336 Atlantic hurricanes. Okay? Find mu. Find mu. And the mean number, right? How did we do it in the regular normal? We had sum up all the observations, divide by n, right? Poisson is different. Okay? And then find the probability. Exactly. It's good that we're saying exactly because we don't have to add up a bunch of them. Find exactly the probability of the 8, where P of x is the probability of x Atlantic hurricanes in a year. So now that I got you this, if you hear that I give you, I want a probability, and I tell you of a time interval, and you see that so many happen in that time interval, you want to use the Poisson. Okay, now, the Poisson, now to calculate the mean, here's the rule. You take the number of hurricanes and you divide by the interval. That is your mean. Your mean is the number of hurricanes, right, divided by the time interval. 336 hurricanes in 55 years. Do you see that? So we now know mu. That's how easy that was. 6.1. Now, guess what the deviation is? The square root of that. Does it get much easier than that? So I hadn't covered this Poisson, so I figured we'd cover it now. So you can put it in an equation, right? So I'm saying, the probability that the random variable takes on exactly 8 instead of greater than or equal or less than or equal, or you see what I'm saying? And we already calculated that mu, right, is here. And if you take the square root of 8, wait a minute, what is the square root of 8? Well, okay, sorry, that's x. There's mu. So what is the square root of 6, somebody? Do you know? The square root of 6. Well, at least he's honest. You. Well, that's 3 times 3. Well, let's try it. I mean, he's on the right track. Can somebody tell me what the square root of 9 is? Okay, can somebody tell me... well, I want to know... What I'm trying to find out is the square root of 6.1, yes? The square root is just a number that multiplied itself will give you that inside number. Okay, so how about, do I know what the square root of 4 is? Okay, so I got an idea. He said 3, but, is 6.1 closer to 4 or to 9? Yeah. So I would expect that this would be something, between 2 and 3. But maybe, I don't know, somebody want to do it? 2.4? I don't know.
2.47.
Oh, not bad. Okay. So, okay. So we calculated mu, yes? And we now got the square root of it. Guess what? Where is the 2.4? Oh, okay. Before I do that, you need to know what E is. Has anybody heard of E? You have? What is E? You don't know? Oh, good. Oh, it's an exponential function. I'm glad you asked. Y, this is a very famous one. Y equals e to the x. It's called an exponential. What's the graph of that look like? Well, what is E equal to? E is approximately 2.71 forever and ever. Very similar to like pi, which is 3.141 ever and ever, and not repeating like 66666. It doesn't have that pattern, right? Okay? So this is kind of interesting. Now, we know that 2.7, for just to think about this graph, let's say it's equal to 3. I want the graph of 3 exponentially raised to the x. Our variable is in the power. Now, how do I always try it? Well, you put a little graph where we have little x guys, right, and little y guys. And I, in this case of being a random variable, I will pick them. So it's not random right now. So I'm going to say 0. Can somebody tell me what 3 to the 0 is? Yeah. Oh. Wait. 3 to the 0 is what? Almost. 1. I know it's weird. Anything raised to the 0 is 1. You're going to see it in all sorts of tests. You'll see a whole bunch of garbage here and garbage, and then they'll raise that to the 0, right? And you'll waste all this time, and it's end up being 1. Do you remember the copying machine when we put it on the copying machine and you put a 0? The machine gets stuck and rolls up the paper, and it looks like a 1 when it comes out. That's how I remember it. But anyway, so this is 1, yes? Okay, what about if I go, now that let's see, x is 1, yeah, that's the part I put. So what do I have now? I want to know what y is. Can somebody tell me what y is when 3 is raised to the minus 1? This ought to rub up a lot of rust off of your algebra. 3 raised to the minus 1, who knows? You know? Negative 9.
No.
It's raised to the minus 1. How would you get a negative 9?
5.
Okay, well, there's another one that's honest after trying.
Negative 3 or negative 1.
Huh?
Negative 3 or negative 1.
This is by definition equal to this. I can ka-chink it. And that negative gets stuck right here. I pulled it down. So whenever you pull it down, remember, like if you have a to the minus, well, let's call it like this. Let's say x raised to the minus a. Yeah, do you see that? It's an a. Okay? And this is x to the minus b. Yes? I'm saying you could write this as x raised to the b over x raised to the a. That's what it means. You can do that. Like, well, I don't need to waste, but you get the idea. Is that it's going to be 1/3. Okay. Now I'm going to go here. Why? Okay. So now I'm going to go to. Well, actually, what I need to do, change this, don't I? I get it wrong. I want x equal to 0. I knew I was doing something wrong. Oh, I'm not on yet. Okay. So actually, I want to set x equal to 0 and y is equal to 1. Okay. X is equal to 0 and y is equal to 1. X is equal to minus 1. 3 to any negative can be dropped under, like pulled under, and as a denominator, and the sign will change. Okay? And now I'm going to put 1. Okay. Can somebody tell me what 3 to the 1? I want 1 copy of 3. What is it? Ooh. And how about 2? Which how much? 9. No, don't add them. The copying machine produces out multiplication. And minus 2? Okay, now what I'm asking you is find this. Y equals 3 to the minus 2. What's that? How can I rewrite it? 1 over 3 to the positive 2. That negative sign gets stuck as you pull it down. See, this is like over 1. Does anybody know what I'm talking about? Anyway, when you pull it down, you have to remember that. It just changes signs. That's a whole lecture in itself, but anyway, I'm just trying to give you an idea of the exponential function. Now, so what I'm trying to say is this 1/9. We have problems here, don't we? It's easy there, but not there. Okay, so what does that look like? Now, you got to know the exponential function. It's one of the more fundamental functions in all science, if you like science. Actually, compounded interest continuously every freaking second, and they're adding the interest back on. So, you know, your investment would go faster than simple interest, or interest is just compounded once a month, right? This is compound continuously. It is E, which is another weird thing for some reason. So let's graph it. I'm going to do it right here on top of this. Okay, now here's 0, okay? When x is equal to 0, what is y? This is y, capital Y, and this is capital X. When x is equal to 0, what is y? When x is equal, what is y? Ooh, good. I figured the trick now. I have to just point to the answer, huh? So it goes right through here. Okay, now, when x is equal to 1. Yeah, right. Look at this. When x is equal to 2. 9. 1, 2, 3, 4, 5, 6, 7. Right here. You see that? What's it when it equals to 3? What are 3 copies of 3? Cha-ching, cha-ching, cha-ching. Somebody multiply that out. 27. Way out there, right? Yes? Now, let's go over to the negatives. Now I have minus 1. 1/3. Yeah? Minus 2. 1/9. You understand? What does that look like? This will forever, ever get closer, but never touch. And it will go like this, and then it's going to shoot up like this. You understand? That is exponential growth. That's what it means when they say it's growing exponentially. Okay? The only difference is that for E, it's 2.71. There are things that are growing exponentially. Over time, I don't know how the human race even survived. We are all members, we are apes because we don't have tails. But we are a member of a family that survived called Homo sapien sapien. Not just sapien, we're Homo sapien sapien, which means we all had the same black mother about 200,000 years ago. We had a black mammy for all of us. And that, including whatever group of husbands or whatever you call them, is what we are now. That's the only surviving hominid of all of them that were existing, and many of them parallel, like the Cro-Magnon, the Neanderthal, the Peking man, the Java man, gone. Okay, we're the only ones. Why? We're pretty damn aggressive. We kill almost everything that we see. We eat almost anything that doesn't immediately kill us. And we're just extremely aggressive. And we're also, I don't know, they asked, because we started eating rotten meat, animals that got killed, we would not necessarily kill it, but we would. And then we got learned to fire so we could cook the meat. So they made it easier to digest protein. And they think that had a lot to do with the brain growth. So, but anyway, the population goes from minus 200,000 years ago, okay? And our population was so low that it was almost constantly, almost zero for years and years. I mean, and maybe if it go back then, it was just, we'd be eaten, we'd be diseased. Yeah, we lived to, maybe if you're lucky, lived to 34. It was just miserable. And we're going along now. We go way, 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 way like here. Guess what happens? Some Hungarian doctor figures out maybe it's a good idea to wash your hands, because they were working with women giving birth. So they use their same dirty hands and stuff, go from one, and all of that good stuff. And of course, they were all dying off, with a high percentage of childbirth. And somebody came out with the next brilliant thing is, how about if you don't eat where you shit or piss? Separate it out. You think, duh. Don't eat where you shit. That's a saying, right? Or don't shit where you eat. Yeah. Or don't crap where you eat, right? That discovery alone, a toilet and all this other stuff, led to this. And penicillin, a couple of good discoveries that we didn't know what a germ was. Louis Pasteur, who helped cure rabies. When that happened, I'm talking about the 200,000 years. We're just talking about the last. This is year 2000. So you go like 109. You understand? And just recently, with that little change, that little bit of education, population growth has gone exponential, to the point that right now there's 7 billion of us. And now there's things called epochs. They're measures of time, large measures of time, right? The Jurassic, these different epochs, right? But they got a new one now that they're going to name Anthropocene, meaning for the first time, man is actually making an impact on the earth. Before they were like kind of rare and indistinguishable from nature and the background as normal nature. Now they're actually affecting global warming. We're actually affecting where we are. So Malthus was an economist, early economist in England, and he said, we are doomed like animals and rats. Rats, for example, they will eat and eat until they run out of food. But I think we're more like bacteria, because bacteria will grow and grow and grow, and they'll die basically eating all their food source, or they die in their own excrement. They suffocate because they're shitting where they eat. And we're kind of doing that with global warming, in my opinion. I don't know who they think they're cheating. You know, even if I was the richest guy on the earth, I still live on the earth. I don't get it. But anyhow, this is the result. And if we don't control population, you're doomed to be. There's a lot of ways to die. I mean, to wipe that back out. The earth would just have to shake a little bit like a wet dog, and we're gone. I'm trying to cheer you up here, but I mean, you don't know. There's several ways that we can be wiped out. I thought I might help. One is methane gas. With global warming, all the tundra in the north that's now melting is releasing all the bacterial, what would you call it, rotting of the grass and things underneath. So it's releasing a lot of methane. But that's not the worst. The worst is if one good earthquake out at the bottom of the ocean, there's huge reserves of methane gas. If that methane, I told him that to cheer him up, I think, if that methane gas escapes, it's big enough that if it ignited, it would burn off all the oxygen in the whole world. So that's cheerful. Anyhow, that's the exponential growth, okay? And it turns out, now this is, I did it of population, right? But the actual exponential growth, y equals e to the x. We already know when x equals 0, there's got to be 1, right? I could just as well do this, y equals 2 to the x, right? And that will go up exponentially, but not as much as 3. Okay? So this guy looks like this. This is the understanding, and I'm just going to let you know this so that when you take the mirror image of this, okay? The mirror image of this guy, or let's try this. If you can imagine me flipping it around, that will look like this. It's the opposite. Of course, I should be the same amount of space away, right? Does anybody know what that function is, by curiosity? I would be surprised if you did, but. Okay, this is y equals the log of base e of x. That's the anti-thing of the exponential function. Logarithm functions always go like this. Logarithm functions will actually keep going up, but slower. And there's a lot of things in biology. Your hearing. Those of you who have hearing, when you go to your stereo and you turn the knob, when you want to increase the volume, that knob is not increasing linearly. It feels like one click, but it's actually the volume control is going from this amount of resistance to this amount to this amount. This is a logarithmic spread, meaning that if this was you want to hear better, you can hear better by turning up the volume, but you start hearing less better no matter how loud you turn it up. That's logarithmic. We hear logarithmically. Okay. There's a lot of things in biology. And notice that's base e, and this is e to the x. Okay. Now, I just give you a little brief thing of what e is. So now let's try it. So what we got is, in this particular problem, in probability, we're using e. So, guess what? Here it is. It's mu. Remember what mu is? 8. 8 factorial. You know 8 factorial? That's 8 times 7 times 6 times 5 times 4 times 3. Yes? Yes? And so, what is this thing? Oh, there's the 2.7. Keep going, right? And guess what mu is? Yep, but it's minus x. It's raised to the... Wait a minute. What happened here? Okay. Oh, here it is. Minus mu. And what's this? That's mu raised to the x. Okay? Can we do that on StatCrunch? Well, I think I did it already. Let's see. I think I'll talk to the designers and have this to be able to switch. Okay. I went to data. Did I? Yeah. Data? No. Strats? I forgot what I did. Yeah. Calculator? We're doing Poisson. How could you forget? And what is the mean? You'll be doing this if you haven't done it already in the homework. What is, now what is it? Well, exactly? No, it said exactly. And there's the graph of it for every possible outcome. And it's okay? Good. I don't know. Was that the answer? I don't know. It doesn't matter. It better be the answer. Okay, so they got, yeah, 0.107. Okay, now, let's do the next distribution. Now, so now, what was next after the Poisson? What do we have? The binomial, the Poisson, the normal, and the uniform so far. Isn't that lovely? Okay, now, I was going to do, now, and now we are back into chapter 6. I covered all the distributions, and now we have the bell curve, and here it is. Okay, let's see. Make sure I get this. So here's it is for the distribution. Y, right, is equal to 1 over the square root of sigma squared pi. Look, pi shows up. Pi shows up. And then, guess what? It's raised to, it's times e. Oh, the exponential function. That's kind of big. I'm going to get rid of this now. Okay. So then we multiply it times e. Remember the exponential function. And what is that equal to? That's like x. Like, remember how we standardized it? We did x and we took away the mean. But in this case, I'm using the population mean divided by sigma squared minus squared. Okay? That is kind of complicated. This is a constant. But it's interesting that pi comes in there and the exponential function. And this is the graph of this. And this goes like this, remember? And this is forever, ever approaching, but never hits. And yet, the area from minus infinity to this is equal to 1. Unbelievable in a way, because this never really hits. So the area is never really finished. It's going forever and ever. So you would expect that the area would explode, wouldn't you? If it never touches, you're adding and adding more area, right? So why should the area under the whole thing be 1? Because the rate of which it's decreases so fast that it's hardly adding anything. And in the limit, we say it's equal to 1, which is perfect for us. And then we use this, right? Remember, we standardized it with the z? Okay, so that is the bell curve. And in this case, we don't often have mu. What will we use? X bar. What is X bar? Add them all up and divide by n. What is S? The sample deviation. Well, that's take every observation, x sub I, subtract x bar. Maybe I don't know. Subtract x bar, and you don't want negative, so you square it, and we divide by n minus 1. Now, okay, and that's going to be S. That you're used to. We've been doing that, okay? Now, if you actually had to do mu, there's a little bit of difference. If you can actually have all the observations of a population, it's the same thing. Look, what did I do here? I added all my x sub i's, And then that result I divide by the sample size, where I goes from 1 to the n. This, guess what that looks like? It's a lot like it, but it's the actual God's mean, where you add all of this up to what? Big N. Good. That's a big good. And this is very similar, except it's like this. Okay, and that's going to be equal. Yeah, you're going to take every observation. Yes? But since we know God's truth, we're going to not subtract x bar, but mu. And that's going to be squared. And now, instead of n minus 1, we're dividing by capital N and square root of that. You can see the similarity. Okay? Good. Now, let me get the next term. The next one here. Let's see. Oh. You remember how we were calculating probabilities between something and something? So, maybe we could try an example. Running out of time. Here we go. How about, okay, if I'm asking you what's the probability, the chart is filling up from here, correct? But if I want to know the interval here, see the interval? This thing's filling up from here back, yeah? And this is filling up from here back. So I have to find the area from here back and subtract this area to get that interval. Bone density. Now, there's a lot of interesting examples, actually. And, okay. Find the bone density, and you want to know is less than 1.27. What is the probability? Women, especially when they age, they have a issue with bone density. Guys can too, but women especially. They take this drug called Fosamax. I don't know if you've heard of it, but it's supposed to kind of help fill in the lost calcium of some sort. And so anyway, this is not an interval. Let's try an interval. Well, let's go ahead and try that. What the heck? Okay, so look, it says table 8.27. Now, do we know the mean here? It says, so we want to find 1.27 on the z-scale. So you may be given one that's not, that you'd have to standardize it to bring it over 0, right? Do you remember the equation for standardizing raw data? Yeah? What was z equal to? To standardize it, we took a particular x, we subtracted whatever, mu, and divided by sigma. Do you remember this? That's how we shifted stuff over the 0. So they're telling us already the z-score, so we don't have to calculate it. So if we go to StatCrunch, so we're going to go here. Oh, well, that's nice. So here's StatCrunch. Is it? Yeah, it is. StatCrunch. Okay. Oh, not that one. Oh, look, finally. That's from your website. Great. Here's all the data from the book. So if you see an example on your e-text and you want to actually run through it, all the ones that we're talking about are here ready to be loaded into StatCrunch. All right. Well, we'll finish the rest later, I guess.